into the, just ended up being transfer a week. So we're right in July already. So today, like we had last year, we're going to have 2 shorter seminars from our PhD students that work on GCC institutes. So today, Ann-Christin will start with her presentation on the rigidly mounted row, and then Victor will follow up with his presentation on the HPGR modeling using DEM. So maybe Arno can introduce Ann. Maybe the structure that we'll use this time is Arno will introduce Ann briefly, and then I'll introduce Victor, and then she presents. And right after Victor presents, and then they can take questions together afterwards. Okay, just in the interest of time to be able to use the best way the 1 hour that we have. Please, Arno.
Yeah, thank you very much, Marcelo, for introducing me. And I would like to introduce Ann-Christin Bottcher. She is a PhD student here at my institute, so Institute of Particle Technology in Braunschweig. She is working on, let's say, more or less element tests to calibrate grinding or milling simulations for different mills. So from mills with loose grinding media, so stirred media mills, for example, but also hammer mills or other impact mills. And she has a look on how we can calibrate breakage function and also breakage probability or breakage rate. And today she will talk about this rigid mounted roller mill, which we developed here at the Institute. And we think this is a really great tool for calibrating such simulations. And I'm also really happy that Victor is presenting, because he was also several months here at our institute. So that maybe also you see that we are really well connected and working together. And that's also a great thing of GCC. Yeah, please, Marcelo.
Yes, indeed, Arno. I think this is a nice matchup because certainly we have been working together, Victor with you in Braunschweig and Ann with us through collaboration and just publish a paper together. And so it is a good example of the cross-pollination between institutes. And indeed, Victor will be presenting right after that. Given his connection difficulties at home, he recorded the presentation, but he's in person here to answer any questions. Basically, Victor is a materials engineer from Colombia, and he went to Brazil for a master's degree with me, where he worked with me and Rodrigo on the mechanistic ball mill model. And after that, he is basically finishing his PhD under my supervision and Gabriel's on the HPGR simulation using DEM, using multi-body dynamics coupling. So you'll be able to see some of his results today very briefly. And really, I hope that there's going to be a nice discussion. So maybe without further ado, we can pass to Ann. Please, Ann.
Can you hear me now?
Yes, now.
Okay, thank you. Yeah, hello everybody. I would like to welcome you to my presentation about single and multiple breakage events and fine particle breakage testing with a two-row mill, which I already, at least in most parts, presented on the comminution this year. And I will start now with introducing the whole topic and giving some insights into what I'm actually doing here. So at our institute, there is an existing model which can, for stirred media mills, which can be divided into a mill model based on the stressing conditions inside the stirred media mill, and in a material model based on the material function, which is actually consisting of the breakage rate and the breakage function. Together, both parameters build the basis for the population balance equation for the stirred media mill. And to actually model the breakage in stirred media mills, it is necessary to obtain the breakage rate either by experiments or by simulation. Furthermore, we would like to obtain the mechanical properties of different materials, such as the breakage function and the breakage strength. And the focus of the talk today is how do we determine the breakage function for particles below 200 micrometer under compression stress. So the breakage behavior of particles below 200 micrometer under compression stress is normally carried out by microcompression experiments. And this is a quite laborious process and some harder materials might jump away. So that is a really useful test procedure to obtain the breakage strength, but it's kind of difficult to obtain the breakage function. Therefore, there's an arising demand and also some expectation towards a new breakage tester, which I would like to shortly introduce you to. So first of all, we would like to have a really high statistical reliability, for example, by triple measurements and a high number of particles tested. The measurement technique should be really fast and easy so that we can process lots of data. Additionally, we would like to test completely different materials, from very soft to very hard ones, and from very elastic to plastic deformation behavior. And finally, and this is the aim, we would like to obtain the breakage function so that we can predict the particle size distribution based on the applied energy. Therefore, we developed a new breakage tester, which enables us to test materials below 200 micrometer under compression stress, based on a 2-roller mill. Here, the material will be transported through a feeding unit, which has been initially optimized via DEM simulation through a funnel on top of the rolls, where we could adapt the gap size from 5 to 180 micrometer. Furthermore, it is possible to change the roller velocity. However, the roller velocity has been set to the particle falling velocity so that the particles are neither accelerated nor broken in a particle bed. During the experimental time, the torque and the line force will be detected. And finally, the product particles are collected in the product removal unit so that we can actually further analyze the material, for example, by their particle size. The focus of the study today is to show the influence of single and multiple stressing on the breakage function, as you can see here below. Therefore, I will shortly start and introduce to you the results from the first stress event. So which effect does the first stressing have on the breakage function, and also how we determined the breakage strength from the 2-roll mill. And then I will go on and show how repeated stressing in a second stress event will affect the breakage function. And in the final part, I will show the results for the size-specific energy, where we have broken the material progressively. During all experiments, the gap size has been adapted so that the gap size to particle size ratio was held constant. Also, the roller velocity was set to the particle falling velocity, which has been measured by high-speed camera beforehand. For the test procedure, we have used soda lime glass particles, which have a really high sphericity and have been sieved into 4 narrow size classes with a Young's modulus of 77 gigapascal and a Mohs hardness above 6 Mohs. The roller velocity was set to 1.1 meter per second, which is identical to the particle falling velocity. To get the information from the line force to the particle strength, we want to draw conclusions from the measured line force to the particle strength. And the particle strength that was actually determined by Schönert-Singer stressing. And he defined the particle strength as the force acting on a single particle at its breakage point divided by the nominal particle cross-section. In our case, because this is a really important parameter for the particles, we integrated the line force and calculated a medium force value, which was then also attributed towards the total number of particles. Furthermore, we included and considered here a residence time of the particles on the rows. Dividing this by the cross-sectional area, we obtained a similar value, which can be compared to Schönert single stressing, and also we can get here the particle strengths and information about what kind of force we need to actually break our particles. The diagram on the left-hand side shows the calculated particle strength for all 4 size classes at different ratios. For the first stress event, the calculated particle strength was increased with lowering the gap size to particle size ratio. At a ratio of 88%, we saw that the plateau is formed and the strength stays constant. This behavior can be related to the plastic deformation behavior of the particles. It was found that this area of stressing is comparable to Schönert single particle stressing. The particle strength shown here is close to 2,500 Newton per square millimeter, determined by microcompression experiments. But how is the particle strength influenced by repeated stress events of already previously broken particles? Our expectations would assume that with a lower feed size, the particle strength would increase. However, it can be seen on the left-hand side that at a second stress event, the particle strength is lowered, even though the particle size is decreased, influencing also the breakage point of the particles. Furthermore, it is obvious that the strength is increasing for the third stress event, but its absolute value sometimes lays below the strength of the initial size. Consequently, particle history plays an important role for its breakage. First of all, previously broken material can be weakened, which leads to the conclusion that the history of breakage influences the particle strength, which is an important information for the breakage function. Second of all, the particles of the first breakage event show a nearly ideal spherical shape, which can be either weakened, ideally broken, or shattered, depending on the applied energy. If such previously broken fragments are now stressed a second time, and they, of course, do not have an ideal spherical shape, it will vary in orientation. In the outer parts of the particle break more easily, and the non-spherical shape offers a totally different target, since the applied forces cannot be distributed as homogeneously as in a spherical shape. All stated points are going to have a huge influence on the resulting breakage function. The breakage function of the first stressing has been determined by the T10-Tn model, which relates the breakage function to the feed size by several base points, the so-called Tn values. Therein, the Tn describes the percentage of material in 1/n of the feed size after breakage. To relate the T10 to the applied energy, we have used the following equation, which is also dependent on the energy applied at the breakage point, which is influenced as previously shown by the first stress event. The Tn values can be calculated by an incomplete beta function. Through the interpolation, it is then possible to determine the breakage function. We could successfully use this to predict the particle size distribution on the two-roll mill. But an open question that has not been investigated so far is, how does the breakage history actually influences the breakage function? Therefore, I would like to explain in the following the effect of a second stressing on the particle size distribution under different gap size to particle size ratios. On the left-hand side, you can see the result for the first stress event, where with a smaller gap size, the particle size decreases with a smaller gap. Comparing this to the second stress event, it can be observed that the particle size decreases as well with a decrease in gap size, but the energy values only increase slightly. Only for a ratio of 28%, the energies increase significantly, which can be attributed to a breakage in multiple fragments due to the much higher energy in the first breakage event. Comparing the breakage of the first and the second stressing by looking at the X50 independency of the accumulated energy, we gain further information about the effect of a first stressing on the second stress event. In general, we can distinguish between two cases. The first case deals with energies below the particle strengths in the first stress event. It is obvious that the particles are weakened so that they can be broken in a second stress event. But the point lays next to each other so that more energy is necessary. At a specific point, the graphs start to line up. This second case shows up if the energies are high enough so that the energy is not only used for weakening the particles, but also significantly breaks them into a lower particle size. In conclusion, energies below the particle strengths weaken the particles and with this also influence the breakage behavior. The two cases affect the particle size distribution and therefore also the breakage function differently. For case one, looking at two similar particle size distributions after the first and the second stressing, two things can be observed. First, the fines are decreased for double stressing with lower energy compared with double stressing with 2 times lower energy compared to one stressing with medium energy. Second, it is much more energy necessary to actually reach similar size distributions. If the first stressing only weakens the particles. In conclusion, weakening decreases the amount of fines and increases the energy necessary. If the particles have been broken in the first stress event, similar size distributions show a different form for the breakage function with double stressing. With double stressing, the width of the distribution decreases as seen on the left-hand side. This is related to the decrease in particle strength. The material has more defects after the first breakage and will break along those. So that extremely brittle behavior and therefore increased fines at the outer diameter of the particle are prohibited. In conclusion, the history of the breakage of a particle is relevant for the breakage function and should be considered. This effect is even stronger if two different feed sizes are stressed in the first stress event, and both are broken into the same size, as can be seen on the left-hand side. This strongly affects further breakage of the particles. First of all, we can observe that the energy to break the particles into the same size is higher for the larger particles. Furthermore, the polydispersity index is decreasing if it's smaller for smaller feed size. If we stress both product size distributions a second time, the particle size distributions do not align anymore, even though the applied gaps are quite similar. It can be seen that previously coarser particles are now broken in even smaller fragments. The form of the size distribution seems to be not influenced, so that a closer look at the resulting X50 may give further insight. As already explained, the X50 after the second stressing decreases if a higher feed size was applied in the first stress event. To break both sizes into the same size, we need to apply a higher energy to the coarser particles. This higher energy causes additional damage to the fragments so that a second stressing is more successful than for the finer feed size. Since all operations so far were obtained for the spherical shape, a second particle system, here basalt was tested. On the left-hand side, the basalt particles were weakened by a high gap size to particle size ratio, and as well tested a second time. Comparing this to a ratio of 78%, the applied energies have been pretty close to each other. Stressing twice with lower energy results in slightly smaller fragments. The shape of the distribution is not influenced. The basalt particles contain much more defects than the glass particles, along which lower energies will induce breakage. Applying higher energies, the form of the breakage changes, the additional energy of the second breakage event induces further breakage of the larger fragments. Furthermore, we have investigated the site-specific energy, which is a quantity to describe the energy needed to produce a specific target size. For this, the applied energy in each step has been divided by the amount of particles below a specific target size in the product size distribution. On the left-hand side, you can see the size-specific energy for 4 different target sizes. The material has been broken progressively, adapting the gap size to particle size of the previous step. Therein, the size-specific energy increases with decreasing gap size, which means that the energy necessary to break the particles further increases with each step. This effect is related to lowering the particle size. Only in the first step, higher size-specific only the first step shows a higher size-specific energy than the step behind. This effect is strongly related to the spherical shape and is also an explanation why the particle strength decreases after the first stress event. Due to the spherical shape, more stress can be absorbed. Furthermore, the size-specific energy increases with a lower target size, so that more energy is needed to produce a smaller particle size. Other than that, the slope of the 4 target sizes is constant, so that in the following, we only show results for 10 micrometer. And finally, I would like to show the size-specific energy for 2 different materials tested on the two-roll mill at a target size of 10 micrometer. The material have been ground progressively, adapting the gap size in each step. The glass particles have been in a similar size range as the basalt particles. Both show an increasing size-specific energy in each step. However, the energy to ground the glass is higher than the one necessary for basalt, which is attributed to a higher particle strength. In conclusion, the size-specific energy is a function of material properties and size. Summarizing the results, breakage history is an important aspect which affects both the particle strength and the breakage function. Specific energies below the particle strength weaken the particles. The number of flaws in the particles are increased by weakening and high energies applied on the particles. The size-specific energy applied on the energy has been calculated, and it was shown that it is a function of material properties and particle size. In the future, we would like to implement a time and history dependent breakage function in the model of the stirred media mill and validate the simulations then by experiments. And now I would like to shortly thank my former student and now colleague Dennis Boysen, who did most of the basic experiments, our technician in our workshop for building the device, the DFG for funding this project, and Exact for their support. Thank you for your attention. I'm looking forward to your questions.
Okay, thanks, Anne, for the great presentation. Without further ado, maybe we can go into Victor's presentation, but well, clapping hands there for Anne.
Kann ich das hier irgendwie beenden?
Yes, Sherry, correct? You will be presenting, showing the recording of Victor's presentation.
Good morning, I'm Victor Rodriguez. I'm a doctoral student from the Federal University of Rio de Janeiro. With my advice to the professor Luis Marcelo Tavares and Dr. Gabriel Barrios, we developed this work entitled Insight into HPGR Performance through Simulation using DEM. So as an introduction, we are going to present what is the high pressure grinding roll, which over the last 30 years, this technology has been evolving, responding to different challenges from industry. It consists in two rolls. One is a fixed one and the other one is a floating roll. It's floating because it's coupled with an hydraulic system which lets open and close this gap and generate a compression under the material and reduce the particle size. We try to simulate this equipment using a discrete element method. This is a numerical method which was proposed by Kuhn and Stride in 1979. It used the Newton equation of motion and a contact model to calculate the trajectories and the resultant forces of the interactions. It was implemented in different commercial software as EDM, Rocky, or PF and PFC. And also there are some open sources like Likes and Jades. One of the most used contact model is the Hertz-Mendel model. This contact model has the advantage of allowing to track the motion and gross kinetics of a large number of particles with good computational efficiency. The normal force is calculated by this expression where an elastic component and damping component are assumed, and the tangential force is calculated by the Coulomb friction law, where the minimum between this term or this term is taken. Here we can see some application of the methods as conveyor belt, blast furnace, hoppers, tumble mills, and but we can see that all these particles, they are not breaking, but it's possible to describe the breakage in the DEM environment. There are different approaches to describe breakage in the DEM environment. What is the particle repellent? One is the particle repellent model proposed by Cleland in 2001 and modified by Barrios and in 2015 and 2020. It consists in a particle is going to be replaced by smaller particles. One is submitted to a determined stress. To the other hand, Potapov and Campbell proposes the discrete grain breakage model, and after they have to simplify by the fast breakage model in 2007. Both are used the polyhedral particle. We can see here the figure a sequence how a particle is going to break. Another approach is the proposed by Potjunen and Kundal in 2004. This is the bonding particle model, which there is a link between the particles, and this is based in the beam theory. Is going to determine when is going to be separated these particles. Jimenez Herrera in 2018 it makes the comparison between this model and concluded that the particle replacement model presents some advantage in computational effort and also to fit into the experiment. So Tavares and Chaga 2021 proposed a stochastic particle replacement strategy for simulate breakage in DEM. The authors describe the particle fracture energy by a probabilistic distribution, and the median of the probabilistic distribution calculated in function of the particle size. Also was implemented the damage in the particle, where the particles can break because of the stress, because of the continuous impact, repeated impact. Fragmentation is very interesting how it was proposed, because it used a set of families which are created as a function of the T10, and the T10 is related with the rest of the ends is related with the modeling using the incomplete beta function proposed by Carvalho 2015. Here we can see an example of that set of families where is determined the relative size of the fragments and the number of fragments or the number of particles that is going to create once the particle break. The author said that with different families, set of families, when you sum all of them, is going to create a more realistic particle size distribution. In the author approach, they propose there are three kinds of particles. One is the resolver particles. These particles could break only if its size, particle size, is 5 times minimum global size. If not, these particles are going to become unbreakable, and after it's going to storage the T10 and is going to be post-processing. Also, there are an additional particle that is the dummy particle, which represents the fineness in each breakage event, and it determined also in the set of families here in the bottom of the set of families. Here determine the number of dummy particles that is going to create a breakage event, and also is post-processing using the Gaudian-Schumann equation when it's in function of this exponent, which also is in function of the T4 and between the radio of the T4 and T75. This model was implemented in application programming interface API, also by the Alter IDEM, and by Tavares. By Professor Tavares. I was part of that work. So HPGR simulation using DM. There are different approaches proposed proposed by Ayres, Queens, Barros, and Tavares, clearly, and recently Nagata. They all using different breakage model, and one of them describe the floating rolls, other just fix the rolls and determine how the breakage is going out there. But there are some challenges, even like this, like the large number of particles in the simulation, accounting for the influence of fine particles in the particle bearer response, the description of the floating roll, and the prediction of equivalent in pilot and industrial scale. So like this, the objective of the present work is develop a methodology to allow DM simulation of HPGR using the dynamic coupling and breakage model. Apply this approach to study the influence of the scene variables on HPGR performance. So to this, we selected the materials and methods used. We selected a material and a critical material. Actually, this is an iron ore concentrate processed in Vale pelletizing plants. This material is very important to Brazil, obviously, but also it's a challenge because look at the particle size is very fine, and also the container moisture. So we try to scale up in DM simulation, scale up these particles. So to that we use some batch scale style, one to determine the material flow, the other to determine the material compression response using the piston as die test. Also, we developed two campaigns in different pilot scale units. One is in the RPR roller press and manufactured by the KHD and installing the complexity run in Brazil. And an additional one was performing in the HRC roller press manufactured by Metso, installing in the facilities in Santiago. The mainly difference is in the confidence system, where a chip plate is used for the RPR and flange is used for HRC. Here in this table we can see the different parameters of each unit, and we change some operational variables as roll speed and specific force applied. So the DM simulation, we use the EDM Alter version 2020.3. It has some advantage or some improvements. One is the implementation of the Tavares breakage model. It was implemented with the no slip hertz milling contact model and with all the characteristics that we already mentioned. Also, it was implementing incorporating some motion controllers that allow objects to react to particle geometry forces. That is very interesting to apply to describe the floating roll in an HPGR. And also we are scale up the particles, so we are using a particle size distribution determined for this fraction presented in this table, and we study the top size of the particle size distribution, changing from 10, 8, and 6 millimeters. In this scheme, we can see the summary of the methodology. First, we calibrate the DM contact parameters through the DM simulation of the batch scale test. Here we try to replicate the dynamic and static angle, repose angle, to change or to select the optimal coefficient of restitution, friction, and rolling. And after this we calibrate using the piston and die test, simulated this test. We calibrate the shear modulus of the particles, the particle repellent or breakage parameters, and also the density of the particle, of the scale up of the particle, to try to match the curve force versus displacement. Finally, we made some preliminary simulation to try to evaluate if the number of particles are feasible to be simulated, and also to correlate the flake density, which have to match with the experimental, and also to calculate the bypass mass flow. Bypass mass flow is the material which is ejected by the bypass gap. The bypass gap is the space between the roll and the confinement system. After this, and with the good match with the experiments, we go to make some performance variables predictions, and study the actual profiles and also the product side distribution. This last one only in a qualitatively way, since we are scale up the particles, so we are not representing the real ones just in a macro way. So we finish the validation stage. We try to describe the influence of the different design variables. We took as a base case the pilot's HPGR with cheek plates and 1 meter diameter and 0.32 in width. We changed the confinement system from cheek plates to smooth flanges, and also flanges with the studs in its surface, as we can see in the figure. We also studied the influence of the aspect ratio. We increased gradually the width of the rolls and maintaining the diameter of the rolls. With these 3 aspect ratio were tested, and also we studied the wear profile in a surface of the rolls. From the literature, we obtained 2 kind of wear pattern. One is the trapezoidal of bathtub. We can see here how it was implemented in the CAD of the simulation, and also a parabolic surface. This one both with a 2.5 millimeters in depth, and also was made an additional with 5 millimeters. Now are presented the results. These are the results of the bench scale handle test and estimation of contact parameters. We can see here the repose angle of the simulation of the KLAS particles. We observe that there are a good agreement, but even like this, there are some limitations of the non-sleep Hertzsmeeden model to describe some adhesion mechanisms inside of the particles to these finds, and also was observed in the tumble mill test developed and simulated. We can see here that we increase the static and rolling friction to try to obtain and to increase that repose angle. But even like this, for the purpose of this approach, we think that is good enough to describe the HPGR simulation. This figure shows the results of the pistons die test. This gray one is the experimental, while the rest of the lines correspond to simulation. All of them, or each one with a different top size in the particle size distribution fitted. And to try to reproduce the experimental, we have to change the shear modulus of the particles, and we can see that the particle replacement model, is able to represent both the lowering curve, the lowering condition, and unloading conditions. We also can see here in this table the particle replacement parameters calibrated also with this simulation. We selected it as top size of 8 mm because it has good resolution and reasonable computational effort when running the HPGR simulation. So, a preliminary simulation were performed. As the particle was scaled up, the bypass gap also have to be scaled up to let eject the same material which actually the experiments are ejected by the bypass. So we took as a criteria the model proposed by Campos in 2019. This model calculates that 27% of the material is ejected by the bypass. So with this, a simulation with 11 millimeters is considered to be the right one, as is similar to the proposed by Campos. And with this, after, yeah, there we performing the rest of simulation, and in this figure we can observe the result of the good prediction of the model. Here we have the throughput, and we can see how the model is in good agreement with the experimental, and also for the power with just 2 points, a little outlier to the experiments, but the rest of simulation was able to predict both key variables, the throughput and power. Uh, when we compare the working gap, we can see a significant difference. The simulation, here we can see all the experiments with HRC. In the experiments, the working gap was not sensitive to the variable changes as velocity and pressure, grinding pressure, but the simulation was. So we think that's more related because of the scale up pressure, and also because of the Hertz milling model, that maybe the grip of the particles of the material is not, or could have some influence that which this working gap is not be the same. But we are very happy that we, even like this, with all this approach, we obtaining these good results and are prediction in a pilot scale. So it's very nice with the DEM model. We also can study how the product side distribution is generated along the rolls. We can say different position here. One is the one of the H, 5 is the other one. They're in the position 3, the center of the rolls. In these figures, all these profiles are compared the predicted ones with the experimental. We can see that in all the cases there are a good agreement, at least in the shape. Of course, the scale of the experimental is different. We can see here the experimental is different from the predicted, but even like this, there are with this we can make some more that prediction. We can make some studies how the different conditions are influencing in the comminution of the particles. So that actually is something that we made in the second stage, where we study the confinement system. So this table shows you the summary of the results. If simulation with flanges presents higher throughput through the rolls compared with the chip plates, and when we use the studio ones, there was the higher between the simulation. We also can see that the power was increased. The power was increasing in the simulation, and the consumption of energy was most favorable for the studied flanges. But of course, as there are more material passing through the rolls, coarser product was observed in with this configuration. We also study how the mass flow rate is distributed along the rolls. We can see similar profiles for all the simulations, but there are an increase in the material ejected in the edge of the rolls. We also can study how the pressure profile is distributed along the rolls. Here the zero position corresponds to the center of the rolls. This is the already pressure profile observed before. We put smooth flanges. There is a reduction in the edge effect, and this reduction was increased because of the presence of the studio flanges. The maximum profiling this was in the center for all the cases, and it was similar between the simulations. This figure shows to us the predicted 45 millimeters, so the particle size distribution of the product particle size distribution. We can observe in these profiles that for chip plates there is coarser for all the cases there is a coarser particles in the edge of the rolls, but that is decreased, or that is reduced, that edge effect, because of the pressure of flanges, and the maximum is in the center, but for these two flanges we observe coarser particles along the rolls, in the center of the rolls. Also we study the aspect ratio. So in this figure we can see how is the mass flow rate distributed along the rolls. The zero position corresponds to the center of all the rolls, and they are increased gradually for each width. Remember that we change only the width in the rolls, and just maintaining the diameter. Simulation with higher aspect ratio, there is a peak here, there is more material passing through the center of the roll, but there appears a drastic drop of the mass flow rate, and after there is an increase because of the material which actually is ejected by the bypass. That's drastically is a little more slight, or more homogeneous for the rest of configuration with lower aspect ratio. We also can study the compression force, how it's changed. We can see in all the cases a similar maximum force in the center of the rolls, with a drop and also a similar H effect. We can observe this H effect, the drop of the pressure in the H. We can see that is the same, of course in a relative way, is more drastically for the simulation or the HPGR with a higher aspect ratio. We also compare the product size distribution, how it is distributed along the rolls, and we can see that for higher aspect radius we observed a peak or finer particles, and which actually is in agreement with the reported by some authors. But it cannot be explained, isn't it? We are seeing the same pressure profile, why we are observed here a peak in this generation of finer particles. We'll actually study this more in depth. So all these pressure profile were performing in this zone, in this first zone that we observe here. So after we try to explain this fact, and we made the analysis in this second zone. In this figure we can see that actually this figure, which corresponds to a compression profile, this second zone, we can see that a maximum of the same peak appears in this zone, higher from that the rest of lower aspect ratio. The simulation suggests that there is a increase in the confinement condition before the compression zone of the in a HPGR with higher aspect radius, which actually means that the nip angle could change because of this aspect ratio. Finally, the roll wear condition. Just to remember the both pattern profiles that we tested. One is the trapezoidal or bathtub, and the other one is the parabolic. We can see here how the mass flow rates is changed along the roll. When in the center we have some homogeneous material passing, and close to the edge there is a reduction of material passing, and after in the bypass zone there is an increase because of the free falling material. Also we can see that as the roll is where there is an increase in material passing in the center, even more to the trapezoidal with 5 millimeters. Also the simulation was able to predict how the force is distributed along the rolls, which because of this where there is a drop in the force in the center of the rolls, and there is an increase in the section close to the edge of the rolls. This result is in agreement with the particle size distribution analyzing also along the rolls, where in the center we observe coarser particles, and here in this zone which there are high stresses, more finer particles are predicted. With this, we finally can conclude that a methodology has been proposed, which bench scale handle test and piston die test allow it calibration of the end and material properties for the simulation. That using this approach, we provide valid prediction of key variables of 2 units HPGR as to the effort variation of the confinement system as per radius and the wear condition of key variables. The simulation also was able to predict the mass flow rate, compressive force, a percentage passing 45 micrometers. And finally, we just have to say thank you with this Brazilian funding institution, as NPQ, CAPES, FAPERGI, and also to the Vale and Altair to the technical support. And thank you for the attention.
Well, thanks, Victor. Thanks, Sherry, for showing that. And so a round of applause to Victor as well. So we can now take some questions for Anne and for Victor, who are here in the audience. Definitely a lot of information from 40 minutes here or so from the presenters. Great job. So we can take questions here. Maybe you can just open your microphone, or you can actually write down. Please feel free.
I can have a question then.
Please go ahead.
Thank you, Professor Tavares. So thank you very much, both of you, for very interesting presentations. I have this question for Ann-Christin. I think it was very interesting to see some of the diagrams, since I was thinking, do you actually propose a test where you would actually not break the particles? So by intention to kind of make these pre-cracks that you showed, and then I think your diagrams were very good in that sense. But are you also proposing that this could be made on a more bigger scale, on a very systematic, with a lot of materials, that you really try not to break them, to be able to better understand the breakage behavior?
Yeah, I think it's. I hope you can hear me.
Yes.
Okay, good. So I think it's actually really good possible to do that on a big scale. So if you use gap sizes which are really close to the size of the particles, they will be not breaking. I don't think so. So in my case, I always had to reduce the gap size to around 68% of the X50. But I know that in some studies at Malcolm's Institute, there were all gap size ratios around 88% used. And if you increase this ratio a little bit further, you see those micro cracks. And right now, and this should come in the paper then, but it's still in work, we do some micro compression experiments on the weakened particles, and we can also see those micro cracks. And there are some particles, or most of the particles, which are still in their original spherical shape, but do have those micro cracks inside.
Thank you, very interesting.
Excellent. Please, Aubrey.
Thank you very much, Christine, and thank you very much, Victor, for the nice presentations. I just wanted to ask Christine a question. The area of breakage is very tricky. For instance, if you go above the grain size for the particles, the rules governing breakage would be very different to when you go sub-grain. Don't you think some of your observations are when you go too fine, you're going to sub-grain size, and what you are seeing is a different sort of rules governing that?
Yeah, so actually we can see some differences in particle breakage if we are coming to finer sizes, and we can increase our sizes a little bit more. And Mark, at least I had a really nice meeting with Shuyat. I hope I spoke it correctly. It's one of Malcolm's students, and at least we discussed that it would be nice to go from really big particles to very small ones to see the size effect from, yeah, like millimeter particles to the submicron range. But it's not done yet.
Excellent. Other questions from the audience?
I have a question for Victor.
Excellent.
Victor, that was a very nice presentation indeed, and the model that is able to predict progeny particles is really wonderful to have. But the question I have is, have you validated what you are producing in that model with some experimental some experiments, and how does it line up, and where do you think the deviation could come from, particularly with your input in terms of material characteristics and also specification of the flow regime in your equipment?
Hello, Professor Aubrey. Thanks for the question. Yeah, we present some validation stage in this presentation. It was in the pilot scale, one with chip plates, and the other unit with flanges. For both throughput and for power, we observed a good prediction of the model. For the gap, we saw that we have some difference, but we think is more. Everyone knows that even in experimental to measure the gap in HPGR, there are some difference, isn't it? So we are really happy with the prediction of the model right now, even with different confidence system and units. The model have been able to predict it. We didn't change the material. We just made the calibration for that material that actually, as I mentioned in the presentation, is an extreme material because of the finer. So, but we are right now we are working to try to test it in other materials and other units and other scale also. Thanks.
Yeah, thank you very much. I think my recommendation is maybe try to do a truncated feed that does not have excessive fines. And when you do that test, it will give you some insights on the flow of material when you have cheek plates or when you don't have cheek plates. The fines have a huge effect of how that bed is set up in the system.
Okay, thank you. Thank you so much for the recommendation.
Yes, thanks, Aubrey. Malcolm, please go ahead.
Of course, I always have many questions lined up. So if people don't chip in, then you get my question. I'll start with Ann Bottcher. Really nice to see how far you've got with that device since I saw you maybe 3 years ago. I can't remember the date now. And you were struggling commissioning and things. So really impressive, detailed work, I think, and I think it proved the value of the effort of being able to do many particles, but a detailed or precise measurement. So that's been really good in getting the force in them. I think that's the question I'd like to ask is, you showed size-specific energy increasing for a particular product size, say 10 micron, as you went to a finer gap, was it? I couldn't quite follow. I was just looking at my notes as you produced more of it, and And I want to know how you increase that. Was it many stages of breakage or one stage with a more reduction in a single stage? How did you draw that line with increasing size-specific energy?
Okay, so actually we broke the particles the first time and then measured the particle size, adapted the gap size, measured tested the material again on the two-roller tester, measured the particle size, adapted the gap size, etc., etc. This is actually, I've tested also a third material and it shows a little bit different behavior. So if I get to coarser particles, my size-specific energy is actually decreasing with lowering the gap size. And I think there might be a size effect, but I think there's some more investigation necessary to actually, round that up perfectly and also show some, like, maybe test two more materials to actually really have a huge effect here. And also, say, okay, it's like that. I think there's some kind of barrier, and at that time, this size-specific energy is increasing with lowering the gap size, and it's really dependent on the target size. And so that's why we also looked at those 4 different target sizes. But it's it took me some time actually to get into what you did and how you calculated the size-specific energy. But it's a really nice technique to actually say something, how much energy you actually need to produce a defined size that we want to reach on that two-roller.
Product, yeah, that just, the work of Ballantyne shows exactly the opposite.
Yeah.
As you get closer, the gap gets closer to the product size, the size-specific energy drops.
Mm-hmm.
So I'll be interested in your continuing work and with the other materials. Okay.
Okay, thanks, Malcolm. Please, Hoge, if you want to pick up.
Yeah, perhaps it goes into the same direction. First of all, thank you very much for the interesting presentation. And I think the idea about investigating the history of comminution process is acting on particles is quite interesting. For me, one point is, and this might be a bit connected to the question of Malcolm, how do you consider the toughness of the material, the micro toughness or the macro toughness, whatever you take, considering the point that if you have a very brittle material, if a crack is initiated, it generates as much energy as required to propagate throughout the material. So the crack is propagating through the whole material. If it starts, the particle is getting broken. So you don't have an accumulation of damage in the material. While if you have a rather tough material, not such a brittle one, then it could be the opposite. You just insert or introduce some energy and then it breaks to a certain extent, and then you have to introduce more energy to break it further. So that is quite material specific. How do you consider this in your models?
So right now we didn't consider it in our model, but the plan is at least, so we want to calculate this fatigue function so that we can see, okay, how is our breakage strength changing? And actually, I think the glass particles are kind of brittle particles, and we can see those micro cracks there. So we really had only, like, I think it really has to be a tiny compression, and then you can also see some or accumulate some damage in those particles. But as you definitely have to test that for every material, and it's not possible to predict that yet. And before we could have a model that could actually predict the fatigue of several materials, we would have to test them, and then we can see how the hardness is actually influencing this fatigue function. I think that's an important point, but I don't even know if I will be able to do that in my PhD thesis, or maybe the next one will have to do it.
I think it's quite interesting, particularly with the class speeds. That's a bit specific thing on the production process of the class speeds plays an important role there, how much internal stresses you have already accumulated in the class speeds. So sometimes a very little energy is enough to break the whole thing into 1,000 pieces. And sometimes with other class speeds, you just break it into 2 pieces. So I think it could be interesting. And with the basalt you mentioned, that could be also interesting, because basalt, depending on, or usually it can be rather tough. So the basalt usually is quite interesting material. So comparing the class speeds with the basalt could be an interesting starting point already. Yeah.
And it's also very interesting because right now I try to use that basalt particles also in the stirred media mill, and it's nice to get some information about the breakage function there as well. So yeah.
Interesting. Thanks.
Excellent, Jorge. Yeah, indeed. I think it's like opening the Pandora box in the end, because this breakage in this size range has been very little understood. And I guess also these weakening effects end up appearing and making things much more complicated than we hoped, I suppose, especially for a PhD. But it's really nice to see work in that area. But indeed, I think a lot of work has to be done to clarify a lot of things that are appearing, but excellent. So maybe a final question, if there is from the audience. We are kind of going over time here, but so last chance. No, Malcolm, of course. Please go, Malcolm.
Good line, Malcolm. So for Victor, I was really interested in that simulation work. It's one of the most challenging areas is to do an HPGR. Direct breakage, the problem of a bed. The point Aubrey brought up, the distribution of the fines affect the bed a lot, which really points to my question. I noticed in your simulations, whether it was force or energy or product size, there was a lot of fluctuation across the width of the roll. And do you believe that's real, or is it a product of having, you know, a few particles simulated in a period? So there were differences of maybe 10% in small zones fluctuating across the roll. Would that be a short snapshot of 1/10 of a second versus 3 minutes of running the roll? I didn't know the time period that you developed that variability.
Yes. Please, Victor. No, I don't know. Maybe is Victor still in?
Yeah.
Yes.
Sorry.
Please go ahead.
Yeah, we of course there are some doubts about it, but we saw a good result. I think we saw that most of the predictions was in agreement with the experiments. Of course, there's that doubt that the Professor Malcolm pointing out. But we think that we are going to see that more in deeper in the next months or research. But actually, with the good prediction and all these approaches, is easy to is feasible to make that simulation even with DM. If you see other approaches, maybe you have to put like 2 million of particles. With this approach, or with the scale up procedure, we just need to put that like 2,000 particles in a pilot HPGR. So it's very we think that is very nice. It's very good to follow that line and try to see if maybe that's it's just some artificial in the methods, or it's a real but right now we don't have that resolution maybe.
But I guess that point is Malcolm raised is the time that you used to do the average. I think it's about a second, correct? A second of operation that you use the average for forces and flows, correct, Victor?
Yes, yes, yes. We saw that after 1 second, 1.5 seconds, the equipment arrives in a steady state. So we think that is good enough to make the comparison and to make the analysis.
Okay, and just to add, Malcolm, I think what you're also seeing is a bit of the stud effect, because there's the stud. The studs are actually not small, 5 millimeters high. In the gap is 10 millimeters. So they do really create a lot of this fluctuation that you can see going up and down in the end of the day.
Okay.
Okay. Well, so I guess we went quite a bit over time. So really, I'd like to thank a lot Ann-Christin for a fantastic presentation. They're very enticing for the public here. I think all GCC centers are very engaged in particle breakage studies. So great one. And thanks, Victor, for also filling in the last minute here. Great also on the DEM side that nearly all of us have been working very actively on. So I guess these next couple of months, we won't be having seminars because I think quite a bit of the people in the Northern Hemisphere will be enjoying their summer. Please do, while we here are in the winter time. But I guess in September, correct? We come back with our seminars for the second part of the year. So thank you all for attending, and thanks the presenters, these and the previous ones, for the fantastic job.
Thank you.
Thanks, everyone.
Okay, thanks everyone. So
Coming.
thanks.
Bye.
See you next time then.
Ann-Christin.
Bye.
Cheers, everyone.
Thanks, everyone.